let's welcome our speaker, Mr. Alexander Gofen, to talk about the Taylor Center ODEs solver as a generator of simulations.
Thank you for coming to this session. I began with that this project of this software first was conceived as purely for science and research, and it started more than 20 years ago as a Taylor solver for ordinary differential equations with special unique features, such as high accuracy, 64-bit mantissa of the native Intel format extended, unique dynamic graphics, including 3D stereo, which should be viewed through anaglyphic glasses, and ability to construct phase portraits for solution or ordering differential equations. Later, I collected many illustrious examples from various fields of applied mathematics, and so finally I came to idea of having something like a virtual laboratory for applied mathematics, which I called Exploratorium. Now let me show you my screen so that okay, so this is yes, sir. Okay. This moment. Okay. So here is my website, and the software page. And this software page gives a lot of features of this software, which I do not touch now because not enough time for that. This is the front page of this. This is one of the typical images of the solution of differential equations. This is the trajectory of three-body problem with some chaotic setting. This software also capable of tubular graphics like this. This is the outline of Möbius surface, and this is the outline of Klein-Bottle. And here is how the software constructs phase portraits.
Do you
like
mind
this.
share the link in the chat?
Say again?
Do you mind share the link in the chat by any chance?
I cannot. All the necessary links already are present in my abstract, which is available on the site.
Okay, yeah, I'm only mentioning this because I'm not sure about the other ones, but on my end, your webpage is dimmed, so it's very blank. I can't really see anything, but it could be just me. Sorry about the interruption. Yes, go
Yeah,
ahead.
I think it may be just you. I'm getting a beautiful picture.
Okay, could be just me. I'm
But
sorry.
thanks for checking.
Yeah. Here is one more phase portrait of a very interesting equation. Here, no, you probably cannot see it, which was provided by Hubbard and Beverly West. And this graph shows how accurate this integrator is because it integrates the separatrice quite long enough, and the difference in the initial values here is just one last digit in 64-bit mantissa, And so it keeps on the separators for quite a long, and finally, well, it's of course it splits, of course. Okay, so that was some outline of the possibilities of this software. So the very method of the very characteristic feature of this software is that it shows not just merely final still image of the solution, but it displays this image in progression, so that in real time as a trajectory of bullets. The resolution of this system will not be able to show that, but the final pictures you did see them on the image of my web page. The very method, the very idea that the pictures are dynamic, so it suggests that this system is good for simulations of simulations of various solutions in applied mathematics, because it's a natural modeling tool. So one of my recent addition to my library of such curriculums for applied mathematics was dedicated to the rigid body motion, classical rigid body motion. That was possible because one of my colleagues, Dmitry Garanin, provided me with the equation for the rigid body motion written in the laboratory system of the coordinates. We will see them in a moment. So, and one of the most amazing effects which I explained in this laboratory work was the so-called Jenny-Bekov effect. Jenny-Bekov effect is one of the cases, classical cases of rigid body motion, when the rigid body is free body. Free body means that it is either fixed in gimbal like this, or it is in weightlessness. So, beginning since 19th centuries, the mathematicians who studied rigid body knew that for the body with three distinct axis of inertia, there is a point of instability. But then they couldn't even imagine what strange this point is. So first who discovered this amazing behavior at this strange point of instability was a Soviet astronaut Johnny Bekov when he was on the space station. Now I will try to show you what he did. So, making some maintenance in the space station, he dealt with a bolt and a wing nut, okay? Mm-hmm. And at certain moment, now the bolt is in my hand, but in the space station, the bolt is fixed into the wall of the space station. So he tried to do something like this. Push it. Okay. Here, my desk is just full. But in the space station, there was weightlessness. It didn't fall anywhere. And so the nut kept spinning as just slept from the bolt. It kept spinning in some continuous way. And what happened next was shocking for Johnny Beck. While spinning, this wing nut suddenly flipped the opposite side. Then again, it kept spinning for 10 or 20 seconds and flipped back. That was, he was so amazed that he, of course, reported it. And then people recall that instability was envisaged already in the 19th century, and they began to look closely how it works. Well, again, okay, so now let's look at what mathematics tell us about the behavior of this wing nut. Again, I have to share the screen. And now I will show you this. This is the differential equations of the rigid body motion for the case of free body. The variables here is eta, psi, phi, and psi. This is Euler variables for the moving coordinates. The first remarkable feature of this system is that actually two of these equations are independent of the third one, our standalone equations. This is eta and psi. These equations, therefore, may be solved separately, and which is the most important, because it's just two variables, we can construct for them the phase portrait. Because the phase portrait in this case has a decisive role. Now let's take a look at this phase portrait. Here is the phase portrait for variables eta and psi. This phase portrait clearly shows that we have some important points. The instability point, which was prognosed in 19th century, is this one. When is my cursor now? When the body is exactly in this point, so the eta and psi are constant, never changing, and psi is the constant spinning of the body. That is what Zenibekov saw in the first moment when the wing nut was just spinning. However, because the point is unstable, after several tens of seconds, this trajectory from here, from this point, it jumps by 8 possible ways from this point to the next point of instability, this or this. There are 8 ways how it can do that. And if I showed you one of the simulation, how the motion dynamically happens along one of these trajectories, which you see here. You see, so some of the trajectories are closed, like here. Others are non-closed. So when wing nut is in this point, it has 8 choices. Either jump here on here, or here on here, or here, or here, or here and here. So, but for what is important for us, for that it jumps from one orientation to the next orientation, and then to the next orientation, and ad infinitum. So the dynamic graph of this picture of this motion would show you that the bullet, which represents the position of the solution at this point, is stable for 10 or 15 seconds, and then it very quickly jumps along one of this curve to the next position, and again stays there for 10, 15 seconds, and then again jumps, and so on and so on. So because of having this phase portrait, and because of having dynamic curve of the behavior of this solution, it was able to clearly understand how this effect of Johnny Beckhoff really works. That was, I think, a very telling explanation of this strange behavior. That was only one of the interesting example in this rigid body curriculum, which I displayed in my site. There is also for some example in the same curriculum. There are interesting examples for a rolling disc. And the rolling disc is, no, you can imagine it like a rolling coin, for example. And there is a very interesting Euler case when the rolling disc rolls on the place, so the center of mass is motionless. And also there is a very well analyzed case of heavy top, the different cases of its behavior. So it's quite interesting material for teaching for undergraduate or graduate students for mechanics. But indeed, the most impressive is different examples in celestial mechanics. Here is now I'm opening my software, and go to demo, and for example, three-body Lagrange case, equal masses. Can you see this? This is three petals. This is final picture, but actually it may be viewed dynamically. I cannot imagine how well you can see it now in dynamic. Okay, you see that it evolves, and the bullets move along the trajectories with accelerations and decelerations proper to the real physical process. There are many other interesting examples in celestial mechanics. In the most advanced areas of celestial mechanics, which were with the most recent discoveries, such as, for example, this is the most, this is unimaginable in the past case of free fall of three bodies, which is periodic. Let's see in the motion. So the three bodies are freely falling, then they engage in some interaction, then they stop again, reaching the final point. They stopped, and they get back to the initial point, so that it's actually periodic motion. This example clearly demonstrates how you can model, how you can simulate complex processes for your teaching of the various topics of applied mathematics. And that is why I invite you all to visit my website to see what is already developed for the for teaching process, And you can join, of course, and suggest your own topics and keep enriching this library of simulation, enriching this Exploratorium.
So
That's
this is, sorry, this is a gentle reminder. We have 2 minutes left. Sorry.
okay. That I'm okay. I'm actually finished. Thank you for your attention, and please ask me questions.
Thank you very much. It's really nice talk. Do we have any questions from the audience?
Sure, I have a question. Very nice talk, very interesting. I went to your website and it said that there's a demo available to be downloaded. Does that mean that the demo doesn't have all the features, or I'm a little confused?
The demo contains just the free version of this software, which
Okay.
is already which already includes over 20 or 200 various examples, but not accompanied with any syllabus. It's just a list of various examples. That's what you have when you just download this software.
Okay.
In order to have an access to some teaching materials with this curriculum which I mentioned, you have to follow another link which I provided in my abstract, which is called Exploratorium. There is word Exploratorium. If you go there, there you will have the full instruction how to install any of those several examples which you need for teaching.
All right. Thank you very much. Very nice.
Okay.
Oh, one other question. What language was this written in?
This software is written in Delphi. Borland Delphi. It was Borland Delphi when I began in 2002. Since then, it changed the owner several times. Now it belongs to a company called Embarcadero.
Can your software solve nonlinear PDEs also?
Say again?
Can your software solve partial differential equations?
No,
Just
absolutely
differential.
not. It is so the Taylor solver is especially efficient and easily implementable exactly for ordinary differential equations.
All right, thank you so much.
Yeah.
Thank you.
PDEs are
Really
so
good.
different. Yes. More questions, please?
One other comment. When I went to your website, it says like the site's not secure. Like I get a warning in my browser window.
Don't pay attention to it. Simply my site was
No, I trust you. Don't worry.
let me explain for everybody. It's important. My site is developed as HTTP, not HTTPS. And the reason why I did it HTTP is it's simpler and it is a passive. It's read-only HTML site. Logically, it is senseless to make it HTTPS because it doesn't ask you to enter anything. No critical information of yours, nothing. It's just a read-only text in which you can just, of course, with links, you can click some links and go to other places. So it's absolutely safe. It's just a read-only station.
Thank you very much.
You are very, very welcome, and you all welcome to contact me via email, which is provided on my site. And if you have any additional questions, or if you wish to establish any cooperation in this area, I would be more than happy to cooperate with you.